What specific problem does the proposed method of rule extrapolation aim to solve in the context of out-of-distribution OOD generalization for language models?
The proposed method of rule extrapolation aims to address the challenge of out-of-distribution OOD generalization in language models by evaluating their ability to maintain consistency with certain rules when faced with prompts that violate some of those rules. Specifically, rule extrapolation examines whether a language model, trained on formal languages defined by a logical conjunction of rules, can still satisfy the non-violated rules when presented with OOD data that has zero probability under the training distribution. For instance, in the case of the language A*NB*10, the model should be able to complete prompts that violate the second rule, R2, while still adhering to the first rule, R1. This method provides a systematic way to assess the compositional generalization capabilities of language models, thereby contributing to a better understanding of their OOD behavior and performance. Ultimately, it seeks to formalize a normative approach to how models should learn and extrapolate rules, guided by principles of rational inference.
How does the proposed algorithm for OOD prompt completion work? Illustrate the algorithm step by step, explaining the roles of the parameters and the significance of the modifications made to the Solomonoff prior.
The proposed algorithm for out-of-distribution OOD prompt completion builds upon the Solomonoff prior by introducing two key modifications to better handle the separation of pre-training and testing phases. First, it conditions the prediction on a pre-training dataset, D, consisting of MI/ID sequences, allowing the model to leverage previously learned information while generating completions for OOD prompts. Second, it models semi-measures as lists of conditionals rather than joint distributions, which accommodates the fact that OOD prompts may have zero probability under the training distribution. The algorithm begins by defining a prior weight, alpha, over all possible explanations, P_ID, which are the conditional probabilities of the next token given the previous tokens. The posterior probability of these explanations is then computed based on the pre-training data, D. This approach ensures that even when the OOD prompt has zero probability under the training distribution, the model can still generate a non-zero probability for the next token by considering the learned patterns from D. The significance of these modifications lies in their ability to formalize a rational approach to OOD prompt completion, allowing the model to extrapolate simple explanations consistent with the training data while adhering to the principles of Occam's razor, thus enhancing its generalization capabilities in unseen scenarios.
Can you provide a concrete example of how rule extrapolation functions in a specific case, like the language $A*NB*10? Walk through the main algorithm steps using this example.
In the case of the language A*NB*10, rule extrapolation involves assessing how a language model trained on this formal language behaves when presented with out-of-distribution OOD prompts that violate one of the defined rules. The two rules for this language are R1, the number of IAs equals the number of BS, and R2, AS precede IBS. For example, consider the OOD prompt BBAAB, which violates R2 since it starts with BS. The model must then complete this prompt in a way that still satisfies R1, leading to a valid completion like BBABA. The algorithm steps for rule extrapolation in this scenario include: first, the model is pre-trained on sequences that adhere to both rules. Second, it encounters the OOD prompt where R2 is violated. Third, the model generates a completion that respects R1 despite the violation of R2. If the model successfully produces a completion that satisfies R1, it is considered to have successfully extrapolated the rule beyond its training data. This process illustrates the model's ability to generalize and apply learned rules in novel contexts, demonstrating its compositional generalization capabilities.
What are the practical advantages of utilizing the proposed normative theory for OOD prompt completion compared to existing approaches in language modeling?
The proposed normative theory for OOD prompt completion offers several practical advantages over existing approaches in language modeling. Firstly, it formalizes a rational framework for understanding how models should learn and extrapolate rules which is grounded in algorithmic information theory, 8 principles, thus providing a more principled approach to OOD generalization. Secondly, the theory introduces a non-parametric prior that allows for the completion of prompts even when they have zero probability under the training distribution, effectively addressing the limitations of traditional models that struggle with OOD scenarios. Additionally, by incorporating the concept of simplicity bias, the theory encourages models to favor simpler explanations consistent with the training data, which can enhance their generalization capabilities. Lastly, this normative framework can serve as a guide for developing and assessing future practical models, potentially leading to improved performance in real-world applications where OOD situations are prevalent.
What experimental methodologies were employed to test the effectiveness of rule extrapolation across different model architectures, and what datasets were used in the validation process?
To test the effectiveness of rule extrapolation across different model architectures, the study employed a thorough empirical investigation comparing 5 architectures: linear models, LSTMs, transformers, state space models, specifically Mamba, and the recently introduced XLSTM. The evaluation was conducted using formal languages categorized into regular context-free and context-sensitive grammars with specific languages such as L_1 equals B alpha alpha text contains even number of A's, and L_3 equals A_10 B_10 n greater than 0 being utilized. The experimental methodologies included monitoring training and test loss, evaluating the accuracy of rule adherence R1 and R2 separately and simultaneously for both in-distribution and out-of-distribution samples, and conducting a small pilot human study for comparative analysis. The results were reported in terms of accuracy and test loss, with a focus on how well models could extrapolate rules when faced with prompts that violated certain conditions. This structured approach allowed for a comprehensive assessment of each model's ability to generalize beyond its training data.
What were the key findings regarding the performance of different models on rule extrapolation tasks, and what implications do these findings have for the understanding of OOD generalization in language models?
The key findings regarding the performance of different models on rule extrapolation tasks indicate that no single architecture consistently outperforms others across all formal languages studied. Specifically, while transformers excelled in context-free and context-sensitive grammars, they struggled with regular languages where LSTMs and Mamba performed better. The linear model demonstrated limited capabilities, often performing at or below chance level. These results imply that the ability of language models to generalize out of distribution OOD is architecture dependent and highlights the complexity of OOD generalization, suggesting that different models may be better suited for different types of grammatical structures. This understanding of model performance on rule extrapolation tasks can inform future research and development of language models, emphasizing the need for tailored architectures based on the specific language tasks they are intended to address.